Good evening, one and all. Today, 10th of June 2023, we are going to start the lecture number 2 in module 5. Overall, this is lecture number 29th in the course of hybrid electric and hybrid vehicles. So, here in the module 5 is actually hybrid drivetrain design. We have seen the introductory part of hybrid drivetrain design. Today, we are going to see series hybrid drivetrain control. There are mainly two types of control. One is called as peaking power source, that is PPS, control of that, as well as thermostat control. What are the design principles of electric coupling? That also we are going to see towards the end of this session. This is a session where every slide is very important. It is quite informative. So keep concentration and try to understand concepts in each and every slide. This lecture is very important. In case of parallel hybrid drivetrain also, there will come the graph that we are going to see now. It looks very complex. So series hybrid, whatever graph we are going to see and whatever flowchart, same things are going to come with minor changes in case of parallel hybrid drivetrain also. So understanding the concepts of series hybrid drivetrain, control for PPS and thermostat is very important. In that case, parallel hybrid drivetrain control and PPS thermostat control we will be able to understand easily. We have already completed the operation patterns yesterday. We have given or we have seen the introductory part of the control strategies. There are mainly two types of control strategies we are going to see today. One is PPS, another is thermostat. So after the basic introduction, we are going to go for the detailed understanding of PPS and thermostat control. This topics may be found in the book of Ehsani, that is module number 8. So from page number 229 the topic starts. This is a slide, it was shown to you yesterday. It says that control strategy is a control rule for series hybrid drivetrain that is preset, that means predetermined, in the vehicle controller and governs the operation of each component. So in series hybrid we know there is a fuel source, there is a engine, there is a generator. They make actually the primary powertrain. Then there is a battery, there is a DC to DC converter. They produce the secondary powertrain. These two things generate electrical power, and their power actually is combined in a stage which is called as a electrical coupler. So series hybrid drivetrain is using electrical coupling. After the electrical coupling, the combined electrical power is given to the electrical motor. The motor is actually controlled by a controller. That motor controller is actually supervised by the overall vehicle controller. Output of the motor is given to the transmission system, and then the mechanical power goes to the wheels. So all these components and their operations are specifically controlled by this PPS control strategy. Vehicle controller, that is overall controller, receives the operation commands. So there are three operation commands: accelerator, brake and direction. These commands are received by the vehicle controller from the driver. That means demand from the driver is actually translated into electronic signals by means of sensors, and they are given to the vehicle overall controller. Feedback signal is generated from different output devices, that is how fast the vehicle is moving. That speed is picked up from the axle, or that speed can be picked up from the wheels, that is the vehicle speed. What is the kind of brake applied, what is the movement of the steering, what is the pressure applied on the accelerator, brake. All these various different signals are picked up by different sensors. They are also fed back to the lower level controller or the supreme controller, which is called as a vehicle controller. There are different parameters for engine, there are different parameters for state of charge and all for the battery. All these things are sensed and fed back to the vehicle controller or sub level controllers time to time. And depending on all the signals and depending on all the command inputs, the vehicle controller takes the decision to use the proper operational modes. Obviously, the performance of the drivetrain mainly relies on the control quality, in which the control strategy plays a different role, and which is very crucial. In practice, there are several control strategies that can be employed in a drivetrain for vehicles with different mission requirements. First, we are going to see the maximum SOC, that is state of charge of PPS, which is also called as a max SOC of PPS control. Second, we are going to see the engine turn on turn off control or thermostat control strategy. Max SOC of PPS control strategy is shown here. You have to produce this diagram in exam. It looks very complicated, but after I explain it in detail, you will find it is not at all complex. It is very easy. So this is a graph. We are finding it's a 2-quadrant thing. So first quadrant is x-axis is vehicle speed, y-axis is power. This power can be divided into 2 stages. So from base 0 up to this stage, which is called as the P engine full. That means engine can produce maximum this much power in the y-axis, which is given by this arrow here. After that, the PPS, that means we know in case of series hybrid there is an engine and there is a PPS. PPS is nothing but battery. So PPS can produce, battery can produce maximum this much power. So this is what is the power generated by PPS. This is what is the power produced by engine. So maximum traction power can be P engine plus P PPS, that is this full thing. So this is the maximum traction motor power. So this you have to understand here. If you are coming in the 4th quadrant, same things you are going to find that from here, from the 0 up to this dark line here, this is actually the maximum electrical braking or regenerative braking. Maximum electrical braking can be this much. It is written here. From here to here, you check this arrow, it is called as P regen. So regenerative power can be actually produced by the electrical power. So from this 0 line, whenever we are falling below, it is actually braking. Whenever we are going above from this 0, it is actually traction. And everything is power. Power unit is watts. So whenever we are talking about braking, this is 0 brake. Now we are coming here up to this point, it is called as maximum electrical brake. But if the vehicle brake is more than the maximum producible electrical brake, or maximum brake asked by the driver is suppose at point C, at that time only regenerative braking cannot produce this much power. So in that case, regenerative braking produce this much power, and PB make is the mechanical power. So P regen is the electrical brake power, PB make is the, B stands for brake, so PB make is the mechanical power. So if sometime driver is asking for total power of C, which is called as a hybrid braking mode, in that case P regen is regenerative braking power, you can find here, and PB make is the mechanical brake power. So this C power, so from 0 to C in the opposite direction of traction, this total power is produced by this much of electrical power plus this much of mechanical power. So this is PCOM. PCOM means this is commanded brake power. This PCOM, commanded brake power, how do we know this is brake power? Because this is in the opposite direction of the traction. So traction means this is vehicle is going in the forward direction, and brake power is applied to stop the vehicle. Here you are finding that it is written maximum regenerative braking power. That means from this 0 up to this point, this is the maximum regenerative braking or maximum electrical brake power, and then mechanical brake power. Together we are actually supplying the overall brake power. So C is the overall brake power, hybrid brake power. This is supplied by regenerative brake and mechanical brake together. Now let us come to the traction side. So what is A? A is written as hybrid traction. What is meant by hybrid traction? Hybrid traction means primary source, that is EG. EG stands for engine. It is written here PEG, engine generator max. So from here to here, this is the max EG, and starting from here to top, this is the max PPS. So if sometimes the maximum traction power is asked like this at this point, okay, at that time engine will be producing this much, PPS will be producing this much, and this total power will be supplied for the traction of the motor. Now you are finding there are two cases explained, case A and case B. Case A, we are here. So what is PCOM, commanded power? That means for driving of the vehicle, the driver is asking for A power. That means A watt power. We are finding that this much maximum power can be produced by the engine generator, so PEG. But power asked is at A level, which is greater than PEG. Who is going to supply the extra power? So that bumper power is supplied by the PPS, that means battery. So if A is the commanded power, you are finding here, A is the commanded power, At that time, engine will give all its power for traction, and remaining whatever is the requirement, that will be given by the bumper source or PPS. So this is the main job of the PPS source, that is whenever the vehicle is climbing the hill, whenever it wants to generate too much of acceleration, in that case only this PPS source comes into action. So A, you are finding that A is a hybrid traction mode. In that case, command power is A, and command power A is given like by this arrow, bidirectional arrow. This PCOM is actually satisfied by PEG plus PPPS. This is the case A. You have to exactly explain it like this only. So what is written here, let us see the object of this control strategy. This is called as a max SOC of PPS control strategy. The object of this control strategy is to meet the power demand of the driver and to maintain the SOC of the PPS at a high level. That means engine will be giving the power, and whenever required the PPS will be giving the power, plus at the end of the cycle we have to see that, or we have to ensure that the battery is also fully charged. That means it should not happen that the PPS source will give the required power and it will get discharged and we will leave the car like that. That is not the case. So we have to supply all the commanded power, plus at the end of the cycle we have to ensure that the battery is also fully charged. That means in next, whenever the vehicle is started, next whenever the power is asked, vehicle will be able to supply that. So we are finding that we have to ensure that SOC of the PPS is also at high level. Generator and the engine set, which is called as PEG, is the primary power source, and the PPS, that is the battery, is the secondary source. This control strategy is the proper design for vehicles in which performance that we have to decide, that is speed, gradability and the acceleration. So if we want a pre-decided speed, if we want good gradability, that means vehicle is going up through a hill, plus proper acceleration, all these things can be satisfied by this max SOC of PPS control for series hybrid electric drivetrain. Vehicle with frequent stop go, that means in city driving patterns, and military vehicles in which carrying the mission is the most important objective. So even if you are in city, even if it is a military vehicle, even if you are on highway, so this strategy, that is max SOC of PPS control, will be able to suffice all the required power to the vehicle. A high SOC level in the PPS, generally the battery pack of the PPS, guarantees high performance of vehicle at any time. So what is the first case? First case is the vehicle is demanding power A. So above this vehicle speed axis it is traction, below this vehicle speed X axis it is braking. So top is action in the first quadrant, fourth quadrant response is braking. Commanded power is A. This much power is supplied by the engine generator, this much power is supplied by the PPS. So A power is given to the vehicle for driving the vehicle properly. In case B, what we are finding, so this much is the demand, so PCOM we are finding is very comparatively less. Okay, PCOM is comparatively less, this is called as a B. So in this B we are finding engine generator alone, it can use the traction. Okay, so engine generator alone can give the power for traction. So you are finding that PCOM is less than PE/G. So this much is PE/G full. Okay, so in this case what we can do is we have to first check that whether this SOC is completely charged or not, battery is completely charged or not. If battery is completely charged, in that case engine generator will produce only the power up to 0 to B. So this is the first condition. We have to first check whether the battery, that is a PPS source, is completely charged or not. If the battery is completely charged, then the engine generator is going to produce power only for B. In that case, whatever power is produced by B engine generator, you are finding that this much, this will be going for the traction purpose. But after checking that battery, if we find that no, battery is maybe 80% charged, so it can be charged 20% more. In that case, the engine generator will produce its 100% power. You are finding that this from here to here, this is engine generator full. So if we are finding first that battery is 80% charged or maybe 70% charged, in that case, though only this much power is required, but in that case engine generator will produce little higher power. So this much power from 0 to this B point, this much power will be given to the transmission for driving the vehicle. Remaining power, that is from B level to this level, okay, B level to this level, this small arrow, which is this thing called, it is called as PPS charging. In this case you had found that this is only PPS, that is in this case the PPS is giving the power to the vehicle for traction. But in this case you are finding that the vehicle is asking for very less power, that means vehicle is running through the highway. It's a very smooth road, there is no banking, there is no slope, okay, and vehicle is not running with too much of acceleration, vehicle is running with 70-80 km/h speed. In that case, with the extra remaining power in the engine and generator, we can run the vehicle plus we can charge the PPS at the same time. So this B, it's also traction, but it's traction with PPS charging. Previously A, you can say it is traction with PPS discharging. In this case B, you are saying that this is traction with PPS charging. But for that only one condition has to be checked, that is the battery was not fully charged from the beginning. If the battery was completely charged from the beginning, in that case this PPS will not be produced. In that case the engine will be producing power partially, so it is called as PEG partial. So this is the second case. Third case is for braking, which is case number C, which I have already explained. So you can say here the max SOC PPS control strategy is dependent in figure A, B, C, D. So A, B already I have explained. So A is demanded traction power, which is greater than the power that the engine generator can produce. So this much power is the power engine generator can produce. In this case the PPS must produce the power to make up the power shortage in the engine generator. Point B represented the commanded power, which is less than the power that engine generator can produce. So you can find this much is the maximum power that engine generator can produce. So in this case PPS does not need to discharge, but in this case if you are finding that the PPS is 80% charged or 70% charged, in that case some power from the primary source will come to the secondary source, that is PPS, and PPS will get fully charged. So it is written here, point B represents the commanded power that is less than the power produced by the PEG, that means PEG full. In this case operation on 2 is used. So mode selection depends on the SOC level of the PPS. If the SOC of the PPS is 70% in case of B, the engine generator is operated with a full load. Operating point of the engine generator with full load depends on maximum design capacity of the engine generator. So if you are finding PPS is 70%, in that case engine generator will produce 100% power, 70% or 80% power will go for the traction, and remaining 30% or 20% power will go to make this PPS 70% to take it to PPS 100%. You never know when this PPS will come handy in use. So in mode 2, that is point B, PEG is greater than PCOM. Hence max part of PEG power goes to the traction to propel the vehicle. Remaining part of the PEG goes to charge the PPS to increase the PPS level from more than 70% to 100%. In point B, when the SOC of the PPS reaches to maximum, that means you are charging the PPS from 70%, when it reaches to 100%, complete EG is channelized for the P command or traction only. That means as soon as you are finding that engine has made the battery fully charged, in that case again the PEG will become PEG partial, because in that case we don't have to give any PPS power to the battery. So in that case engine will downgrade its output power. So it is very important that when the SOC of the PPS reaches to maximum, that means PPS becomes 100% or to the top line, this is called as a top line, complete EG is channelized for PCOM or traction only. Now PEG does not charge the PPS anymore. The PEG to PPS link remains idle. So this is the second case. At point C, third case, we have already explained commanded braking power is lot greater than the maximum regenerative braking power. Regenerative braking power is electric braking, but commanded power is greater than the electrical braking. In that case the residue or remaining power will be provided by mechanical power. We know that mechanical power is actually a lossy kind of a power. It actually reduces the efficiency of the overall system, but then also as the too much power is asked from the vehicle, only the electrical braking cannot suffice that much power. So in that case we have to take the help of mechanical power. In case of case D, okay, where we are finding that commanded power is lot less than maximum regenerative braking power, that means maximum electric power. In this case only the regenerative power, P regen, you are finding here, D is regenerative braking power. So whenever the demanded power is little less, demanded braking power is little less, in that case only the regenerative power will suffice or will be able to supply the braking power to the vehicle. So main braking power is generated by electrical motor braking, that is P regen or maximum regenerative braking. The mechanical braking system produces the remaining brake power. Point D, they have explained, represents the case where the commanded braking power is less than the maximum braking power that motor can produce. So in this case regenerative type electrical braking is the only used, because we are finding that maximum electrical braking can be this much, ordered or commanded power is this much, it can be supplied only by the regenerative brake. So this explains all the 4 strategies of max SOC of PPS control strategy. Very important thing, it looks very difficult kind of thing, but with little practice and direction of arrows and knowing the things properly, you will be able to explain each of this thing very carefully. And whatever small theories are written in exam, you have to write theories in more detail. This can be another question, that is we can explain the whole process by means of a flow chart. Okay, so previously we have explained the whole thing by means of a graph. That is easier, but you will find that if you can draw this graph, you can do the explanation far better. So that graph and flowchart will not be asked together in one question. So either we have to ask the graph and explanation, or flowchart and the explanation. So let us see the flowchart of the whole process. Okay, so there are 4 modes A, B, C, D. I have not mentioned A, B, C, D here. I have mentioned, so I have added some animation here. As the time goes by, the animation of point A, B, C, D will come here. So you have to be careful that where this A, B, C, D is appearing in this flow chart. So first let us understand the flow chart. So we are starting with 2 actions, traction power command, that is P traction, or braking power command, that is P brake. So inputs are coming from the brake, inputs are coming from accelerator, inputs are coming from the direction. Depending on that, we have to understand whether it's a traction thing. Traction thing means taking the vehicle forward, or it's a braking thing. So braking power command P brake, which is coming from the brake sensor. Traction power command P traction, which is coming from the accelerator sensor. So we have to decide whether it is traction or brake. Depending on that, our next course of action will be decided. So is it traction? So this is a decision box. Is it traction? It is saying no. Okay, it is not traction. That means it will go into the brake domain. So whatever C and D you have found, that will go in this side. But is it traction? Answer is yes. That means we are coming below. So this below this whole 2 boxes, they are actually decision boxes. They are actually for traction. That means A and B will come somewhere here. Okay, and question asks is traction. Is it traction? Answer is no. If not traction, that means what? Braking. That means we are in the 4th quadrant. That means the C and D will come here. I guess it is understood. Again, I am telling you the same thing. So first we have to decide whether it's a traction or it's a braking. So it is traction power command and brake power command. And the question asks is, so both these inputs are given from the sensor, whatever inputs are coming to the vehicle controller. This is actually vehicle controller. Here we are asking the question traction. Answer is yes. So in traction there are 2 modes, that is mode A and mode B. We have to see whether commanded power is greater than the PE/G, or commanded power is less than PE/G. So this course A and B will come here. Okay, if it is not traction, that means it is braking, though whatever happens in the braking, that is C and D, that will come here. So first let us see what is traction. So traction, yes. If the traction is yes, then we have to see engine operator power PE/G and P traction. P traction is nothing but P command. So whatever is the commanded power, that is less than engine power. That means this is case B if it is yes. So traction power, that means commanded power is less than the engine power. And if it is no, that means traction power is greater than engine power. So in this case, what you will find that traction power is greater than engine power, that means commanded power is greater than engine power. In this case, what you will find is we require a hybrid traction. What is hybrid traction? In this case, PPS and engine generator. So PEG and PPS, they will act together. So this is case A. I again show that here P traction is less than PEG. Yes, if yes, that means only the PEG will be able to drive the vehicle traction power, but no means the vehicle, whatever command it is giving, that means command power by the driver, it is greater than PEG power. That means here the PPS has to supply some power. So that's why this is called as hybrid traction. That's why it is called as a mode A. So no means it is hybrid traction. Yes means it is only engine based traction. So when it is only engine based traction, in that case we have to again see this is the SOC of PPS. I told you that whenever the traction power is less than the PE/G, first thing we have to check whether the SOC of the battery or SOC of the PPS is full or not. So in this case we have to see that if SOC is less than SOC top means battery is 100% charged. If the battery is 100% charged, in that case so we can see here that if SOC is less than SOC top, answer is yes. That means there is still scope for PPS to charge. So in this case the PPS charging will happen. This is actually the case number B. If SOC is less than SOC top, answer is no. That means the SOC is actually fully charged. SOC is less than SOC top, answer is no. That means there can be two cases. Less than is not satisfied means either is SOC is equal to SOC top or SOC is greater than SOC top. SOC cannot be greater than SOC top. That means in this case what we are finding is SOC is equal to SOC top. In this case only the engine generator power will be sufficient to drive the vehicle. So the first case whenever in traction we are finding that traction power is less than PEG. If it is no, that means traction power is required power is greater than the engine generated power. In this case hybrid traction will take place. Engine generator and PPS together, they will supply the traction power required by the vehicle. If we are finding that traction power is less than PEG, what is yes, then there comes a second action. In this case we have to check whether SOC is less than SOC top or not. That means battery can still receive some energy or not. If they say yes, SOC is less than SOC top, that means the battery can still take some kind of charge from the external. In that case keep on charging the PPS, which is case B. If you are finding that SOC is equal to SOC top, because SOC cannot be greater than SOC top, in this case no need to charge the battery again. In that case only the engine generator power will be able to produce the traction power. So this is A and this is B. Now go again to the top and just compare the traction and braking power. Okay, we are asking if it is traction or braking. Is it traction? Answer is no. Answer is no means it is braking. It is braking. In that case we have to see this is the maximum motor power, that means PM max. So in this case we are asking that P brake is greater than PM max or P brake is less than PM max. We are finding that the P brake is greater than PM max. What is PM max? PM max means whatever is the maximum power the regenerative or electrical braking can produce. Okay, so the required power, so P brake means this is called as a required braking power or commanded braking power. If the commanded braking power is greater than maximum motor power, maximum regenerative power, in that case we understand that we have to go for hybrid braking. So first we have to understand that we are in the braking mode. In the braking, if the commanded braking is greater than regenerative braking or not. If the answer is yes, we understand that only the regenerative braking, which we were showing by P regen, here we are showing it by PM max. So in that case PM max is not sufficient enough to supply the P brake. In that case we have to go for hybrid braking. What is meant by hybrid braking? It will be PM max plus PB max, which is nothing but the electrical braking plus mechanical braking. But if you are finding that P brake is greater than PM max, if it is no, that means PM max actually is greater than P brake. That means braking power required is less than the electrical braking. In that case only regenerative braking will do, and this case we will call as the D case. So this is a flow chart where all the four cases A, B, C, D they can be explained very easily by means of this flow chart. So whenever you are trying to show this thing, you have to show it in detail and you have to mark this A, B, C, D properly in your flow chart. Only you have to mind that in the book of Ehsani this ABCD are not written clearly, so you have to understand properly and you have to mark the ABCD, and for that you have to see the PPT which is uploaded in Google Classroom with this lecture link. So ABCD you have to see from my slides, otherwise this flowchart you will get in the book of Ehsani module number 8 I guess. So this was the type 1, this was the type 1 control which is called as a max SOC of PPS control strategy. Next we are going to see engine on off thermostat control strategy. Okay, so max SOC of PPS control strategy emphasizes on keeping the SOC of the PPS at a high level constantly. So never we should see that PPS is lagging charge. So as much as possible we have to see that the PPS or the battery it is fully charged. But in some driving conditions such as driving for a long time with a low load on a highway at a constant speed, we can find that the PPS can be easily charged to its full level and the engine generator is forced to operate at a power output smaller than its optimum. That means you have to remember the case B. In case B what we are finding is suppose the PPS was 50% charged, that means PPS was had discharged by 50% or maybe 70%. Here we have written PPS, so this is a graph you are finding, this is the PPS bottom line. That means PPS has got discharged up to 70%, but we want to keep PPS at 100%. So this charging can be done at the simultaneously when the vehicle is running with a low load. That means the vehicle is on a long highway and it is driving for a long time on a highway at a constant speed. Highway, this word is having very big meaning. That means generally highways are having no inclinations. Okay, so highways are made like that. Their actually inclinations are avoided. So whenever the vehicle is on highway on a flat plane and road condition is very good, that means the bumper power requirement is not there. That means we are not requiring any power from the PPPs. That means this is kind of a case B, where the demanded power is lot less than engine generator power. In that case what we can do is, as engine generator is not working to its full potential, in this case we can produce full maximum output power from engine generator. Whatever is power required by the traction that we can use, remaining power we can give to charge the PPS source. So this is the case where engine on off or thermostat control strategy is used here. So this is thermostat is nothing but a thermal rheostat where the thermostat decides when to go on and off. So we can keep a thermostat there and the on off of the PPS we can control by the thermostat. So what happens here in this case, if you see the bottom thing, so this is engine operation, that means operation of the primary source, and this is PPPS SOC. That means you can say charging and discharging of the secondary source, that is the battery. So whenever it is here, that means PPS is 70% charged, that means PPS is 30% discharged. When we are here, at the time you are finding is PPS is 100% charged. So our target is to take the PPS to this level. Whenever the PPS is so for that actually we are using engine. So in this case you are finding, so x-axis is always time for both these graphs. In exam also you have to draw this kind of graph. Maybe you don't need to draw 3 cycles, 1 or 2 cycles will do. Okay, so here we have shown 3 cycles, 1 or 2 cycles also will do. What we are doing is we are initially turning the engine on. As soon as the engine is on, PPS is off. That means in this case you have to understand one thing, that is both the sources cannot act together. Okay, so initially engine is on means primary source is on. In that case we are finding that PPS is very less, that means 70% charged. So when the engine is on, engine is actually doing 2 work. One is engine is giving power for the traction, and at the same time engine is charging the PPS source. So you are finding that as long as the engine is on, which is like a binary kind of a thing, at this point again suddenly you are making the engine off. So in this first region of engine on, you are finding that engine is doing 2 work. It is giving the main power for traction to the vehicle, as well as it is charging the PPS source or battery. And after this much time, engine on time, you are finding that the battery is charging up to the 100%. As soon as the battery goes to the 100%, what we are doing is engine is off. So this engine on and engine off, or PPS off and PPS on, is actually done by a thermostat based control. That's why it is called as a thermostat control strategy. So here the efficiency of the drivetrain is reduced. In this case the engine on off or thermostat control strategy will be appropriate. So as long as engine is on, PPS is off. At this point the engine has gone off. As soon as the engine has gone off, PPS is on. That means this is the secondary storage which is now supply the traction power to the transmission and wheel system. So at this point exactly, PPS is on, engine is off. In that case the secondary source PPS, it is supplying the whole power to the transmission, which in turn takes the tractive force to the wheel. How long it goes? It goes on for this much period. So this is the throw, or this is the period for which the PPS is on, and then we are finding that after this much period the PPS is coming to again 70%. And this is a pre-decided strategy, that is we don't want the PPS to go below 70%. So 70% is the minimum discharge limit. Beyond that you should not take the PPS level less than 70%, because that is not good for the health of the PPS. So this we have to pre-decide. So there is also an algorithm going on. What happens as soon as the PPS touches 70%, the thermostat again will do what? It will make the PPS off automatically. It will turn on the engine automatically. Again, as soon as the engine is on, engine is going to do two work. First, it is going to supply the traction power to the vehicle, and then it is going to charge the SOC, or charge the PPS, and increase its SOC. So again you are finding that in a different path the SOC is getting charged, and after this much time, what is this much time? As long as the engine is on, after this much time you will find that the PPS is reaching to its 100% again. As soon as the PPS is 100%, the thermostat is making the engine off. That means primary source is getting off. In that case the PPS is on. That means for this much period, as long as the engine is off, PPS is going to discharge, and PPS is going to supply all the traction power to the transmission and vehicle. And again in the next stage, as soon as the PPS comes to 70%, what the thermostat is doing is it is switching the PPS off, making the engine on, and the process goes on. So here the efficiency of the drivetrain is reduced, what they are claiming. In this case the engine on off or thermostat control strategy would be appropriate. So the operation of the engine generator is completely controlled by the SOC of the PPS. We find here, as long as the SOC is less than 100% initial case, that time engine is on and PPS is off. As soon as the PPS is becoming fully charged, we are switching off the PPS, we are switching off the engine. So switching on the PPS and switching off the engine. In that case the PPS is going to supply all the traction power to the transmission and wheel. So the operation of the engine generator is completely controlled by the SOC of the PPS. So thermostat is kind of a sensor actuator. When the SOC of the PPS reaches its preset top line, the engine generator is turned off by the thermostat. Vehicle is now propelled only by the PPS or the secondary source. On the other hand, when the SOC of the PPS reaches its bottom line, so bottom line is pre-decided 70%, the engine generator is turned on. Okay, the engine generator will turn itself on. Last line, the PPS obtains its charging from the engine generator. So PPS is obtaining, so in the as long as the engine is on, PPS will get charged from the engine generator. In this way the engine can be always operated within its optimal efficiency region. So engine generator will always keep on charging the PPS as long as the engine generator is on, and when the engine is off, engine generator is off, at that time PPS is going to run the whole show. This is the second on off control, or engine on off or thermostat control strategy. Here thermostat is used for switching on and off of the engine and PPS. And PPS and engine, we have to see the supply, who supplies the transmission power. It is kind of a exclusive, either engine supplies the transmission power or PPS supplies the transmission power. So they cannot supply the power together, because in this case, first a disclaimer, we had said that the vehicle is running on a highway or vehicle is running with a lesser load. Okay, so you cannot say that, sir, when the vehicle is running on the hill, that case is not for engine on off or thermostat control strategy. So thermostat control strategy is applied only when the load on the whole system drivetrain is less. That means the vehicle is running through a flat road, vehicle is running through the highway, vehicle is running through a long highway. In that case only this engine on off thermostat control is applied. Let us see now design principles of a series hybrid electrical coupling drivetrain. So successful design of the drivetrain. So what is drivetrain? Drivetrain is nothing but the combination of two powertrains. So there is a engine generator powertrain, there is a battery powertrain. Together they are producing the drivetrain. So series electrical coupled hybrid drivetrain. Successful design of this drivetrain system means ensuring that the vehicle is capable of achieving design performance such as acceleration, gradability, high speed, high operating efficiency, etc. Electrical coupling device, traction motor drive, engine generator unit, PPS, all these are major design components of the concern. Their design should be primarily considered at the system level and ensuring that all the components work harmoniously. Design of electrical coupling device, there is a very big thing. Power rating design of traction motor, another important thing. Power rating design of the engine generator. Okay, so these all are very important things, and most important is design of the secondary source. What is secondary source? It's battery, but it is called as a PPS. In PPS, what can you design? Power capacity of the PPS and energy capacity of the PPS. So energy capacity means how much maximum energy it can save. This is what is called as energy capacity. What is meant by power capacity? Power capacity means whenever it is giving output, that means when it is discharging, at what faster rate the PPS can discharge power. So while storing the energy, we have to check what is the energy capacity of the PPS, how much maximum energy it can store, and power capacity actually is a output capacity, that at which fastest rate the PPS can discharge. So design principles of electrical coupling device. In this case, we are going to see there are mainly two kinds of connected power source and sink. We are going to see here. So this can be also a 10-mark question. Here it is said that this is a driving command. There are three driving commands, that is acceleration, brake, and direction. So this is a vehicle controller, overall controller. So it is controlling engine, it is controlling generator. Then there is a rectifier, because generator may be producing AC, the motor can be DC. So generator is giving the three-phase AC power, so it can be a three-phase rectifier to a DC output. And here is the PPS. So between the PPS, directly the PPS output power is connected to this bus. So this is a bus which is connecting the rectifier output and PPS power, staying the power to the motor controller. Motor controller is again connected by the vehicle controller. So here you are finding vehicle control is controlling mainly three things: engine operation, generator operation, and motor controller operation. That is the power electronics. So together this power, DC or AC, whatever, it goes to the motor controller. Through it, the motor controller gates it properly. Through that gating, the power is given to the motor. So this is how the motor controller is controlling the speed of the motor, by controlling how much power is to be given to the electrical motor. So this is called as a directly connected power source and sink. So who is the power source? Power source can be generator, power source can be PPS. Actually not generator, power source can be engine, and power source can be PPS. They are directly connected. In this case, you are finding it is directly connected. And then the total power actually is given to the power motor controller. Then motor is connected to the transmission, and then they are connected to the wheel. But you are finding it is directly connected power source and sink at this point. This is actually called as this point. That means power source and sink are connected directly. So electrical coupling device is the sole linkage point for the combining the three sources of the power together: engine, generator, PPS, and traction motor. So this is this point. Its major function is to regulate the power, that is electrical current flow between the power sources and the sink. Who is sink? Sink means who is receiving the power. So motor is the sink, or motor controller. Through it, the sinking is controlled. Okay, so major function is to regulate the power and electrical current flow between the source and sink. The power regulation is carried out based on the proper control of the terminal voltages. So generator output, rectifier input, rectifier output, PPS output, that is the battery output, voltage given to the motor, all these things are the main things that are to be controlled. Simple structure is to connect the three terminals together directly, as shown in the figure right above. So you are finding that all the terminals are connected here. And what are the things vehicle control is controlling? It is controlling all the sources, and it is controlling motor controller, generator, and engine. Design principle of electrical coupling device. So this configuration is the simplest and has lowest cost. Same thing whatever is shown in the previous slide, that thing, but there is a little modification. What is that modification? If you see, the modification is this, that is a DC to DC converter. Previous case, I am showing the previous case, there is no DC to DC converter. PPS is connected to the rectifier output. That means the primary source link and the secondary source link, they are directly connected. That's what is called as a direct connected power source and sink. In the second case, you are finding this is the primary source. That means engine, generator, rectifier together, they are giving the DC power here or AC power, whatever, depending on the type of the traction motor. And PPS was here, but the PPS and bus, in between that there is a DC to DC converter. This plays a very important role. And what is the importance of this thing? We are going to see in the subsequent slides. And question can be asked, which of these two configurations, that is DC to DC converter indirect with PPS and directly connected power source and sink, which of these two configuration is better? So now we are in the second configuration, which is saying configuration with DC to DC converter on PPS side. Here there was no DC to DC converter. In the second case, there is a DC to DC converter, and it's actually with the PPS. So this configuration is the simplest and lowest cost. Its major feature is that bus voltage is equal to the rectified voltage of the generator and that of the PPS. So bus voltage is equal to the rectified voltage of the generator and PPS. That means total bus is rectified voltage from the generator and the voltage of the PPS. Previous case also it was like that. Bus voltage is determined by the minimum of the two voltages, V generator and V PPS. So in this case, the bus voltage is determine the minimum of the two voltages. So if engine is producing 5 volt, if PPS is producing 3 volt, bus voltage will be 3 volt only. Okay, so this is a parallel connection. In that case also it was a parallel connection, but in this case the bus voltage is determined by the minimum of the two voltages, V generator and V PPS. Power flow is solely controlled by the voltage of the generator. Whatever is the voltage of the generator, that will be controlling the power flow. To deliver its power to the traction motor and or to the PPS, the open circuit voltage or zero current of the generator rectified must be higher than the PPS voltage. So these are some of the conditions which are applied. This can be done by controlling the engine throttle or the magnetic field of the generator. In regenerative braking, so regenerative braking means from the traction motor, the power will come to the motor drive through DC to DC converter, it will come to the PPS. Regenerative power can never go to the engine because there is no path for that. But from the traction motor through the motor drive to the DC to DC converter, regenerative power can come to the PPS. So some discussion about the regenerative power also here. In regenerative braking, the generated bus voltage by the traction motor must be higher than the PPS voltage. However, the voltage generated by the traction motor is usually proportional to the rotational speed of the motor. So design principles of electrical coupling of the device. So this is actually the third configuration. I'm sorry, initially I said there are two configurations, but there are actually three. In first configuration, it was direct, engine and PPS was getting connected directly. In the second configuration, PPS and DC to DC converter, they were in series, they were connected to the bus. In this case, the DC to DC converter actually is connected with the engine generator rectifier side. So adding a DC to DC converter and thus releasing the voltage constraints may significantly improve the performance of the drivetrain. Two alternative drivetrains are shown in figure 2 and 3. In configuration 2, that means when the DC to DC converter was with PPS, the DC to DC converter is placed between the PPS and the DC bus, and the engine generator rectifier is connected directly to the DC bus. In configuration 3, the DC to DC converter is placed between the engine generator and the DC bus. You are finding it here. PPS here is directly connected to the DC bus. That means PPS, it is not having any buffer in between, it is directly connected to the DC bus. So in this figure 3, the PPS voltage can be different from the DC bus voltage, whereas the rectified voltage of the engine generator is always equal to the DC bus voltage. So whatever is the engine generator rectifier output, that will be converted to by DC to DC converter, and that will be nothing but equal to bus voltage. So whatever is the voltage of PPS, that matters little less. Contrary to the configuration 2, the DC to DC converter in configuration 2, conditions where rectified voltage generator PPS is always equal to the DC bus voltage. That means one thing we are finding here, wherever the DC to DC converter is there, that source will dictate what is going to be the bus voltage. So DC to DC converter, as it's a buffer, this actually decides the level or condition of the DC bus voltage. Among these three, which one is a better configuration? So why is coupling to better configuration? So here we are finding that this is the coupling. So coupling 1 is not good at all because there is no DC to DC converter. So DC to DC converter actually controls the DC power given to the motor drive. So either 2 or 3. So this is the case number 2, where the configuration with DC to DC converter is towards the PPS side, and this is configuration 3, where the DC to DC converter is on the engine side. The question is asked, which of these two is better configuration? That means 2 or 3. Configuration 2 seems to be more appropriate for series hybrid drivetrain when compared with configuration 3. The advantages are given below. That means if the PPS and DC to DC converter is together, and that is adding the power to the DC bus, which actually we have shown in case of all series electrical hybrid drivetrain, that is the best configuration. Why? There are mainly 5 points you can go through. So changes in the voltage of PPS do not affect the DC bus voltage. So if the PPS voltage suddenly changes, fluctuates, it is not going to affect the DC bus voltage because there is a buffer in between, which is called as a DC to DC converter. Energy in the PPS can be fully used. So this battery energy can be fully used because DC to DC converter is going to pull it from the PPS and then add to the DC bus. Voltage of the DC bus can be maintained by controlling the engine, throttle and or magnetic field of the generator. So actually the controlling of engine, generator and rectifier is happening through the controlling of the engine and generator part. And the generator control can be done by its separate control, electrical control. Engine control can be done by controlling the throttle valve and or the magnetic field of the generator. So for engine there is the throttle valve control, for generator there is a field control. So too many controls are already there. If you are talking about rectifier, we can have a SCR rectifier, we can control the gate of it. So too many controls are already there in case of engine, generator and rectifier control. And this PPS voltage control will be controlled by the DC to DC converter. Low PPS voltage can be used, which may lead to a small and light PPS pack and less cost. And the last thing is the charging current of PPS can be regulated during the regenerative braking and the charging from the engine generator. So we are finding that out of these two configuration, that is where the DC-DC converter should be placed in series with PPS or DC-DC converter is placed with series with engine generator, we are finding that the second configuration is the best one as far as series hybrid electric drivetrain is concerned. So mainly 3 questions, 4 questions can be asked in this whole thing. The first question which can be asked very sincerely, that is what can be the types of series hybrid electrical power control. So there are mainly 2 strategies. One is maximum SOC, another is thermostat based turn on turn off. Then one 10 mark question can be asked on this max SOC and PPS control strategy. You have to explain all this A, B, C, D, all this 4 things with respect to the graph. Then there can be a next 10 mark question, that is you have to explain all these 4 cases A, B, C, D, and with the help of the graph you have to show that whether it is traction or braking first. If it is traction, then you have to answer these 2 questions, whether the traction power is less than engine generator power or it is greater than engine generator power. If it is less than, then strategy A, that is hybrid, if the traction power is less than engine generator power, in that case you have to go for case B. Or if the traction power is greater than engine generator power, in that case you have to go by strategy A. If it is braking, then you have to see whether the braking power command is greater than the PM max, that is a motor or that is a electrical braking power. If the required braking power is greater than electrical braking, in that case you have to apply hybrid braking, electrical mechanical together, that is strategy C. If the required power is less than motor power, in that case you can go for strategy D, right? Likewise like that. So this can be also asked as a 10 mark question. In that case you have to explain ABCD in full. Some part of the previous graph you can show and then you have to explain, and then you can go for this flowchart. Then there can be a 5 mark question on engine on off thermostat control strategy. It cannot be a 10 mark question, and you have to say that this on off of the engine and PPS, it can be done by means of a thermostat. Last question, that is what are the 3 different control strategies for electrical drive coupled design, and it can be actually a 5 mark question, where to place the DC to DC converter to get the maximum control and why. Okay, so this last slide also, if you prepare, you can answer this 10 mark question. So you have to write this 5 answers, and you have to explain that why the configuration 2, that is DC to DC converter with PPS, is a better configuration than DC to DC converter connected with the engine, generator and rectifier. So prepare all these questions for this lecture. This is going to be a very big lecture. Every slide is very much important, and prepare all these slides very properly in this lecture number 29. That's all from today from me. Thank you.